Consider the humble helium balloon. Now, you can turn helium from a gas into a liquid, but what on earth is holding those helium atoms together? What is the intermolecular force in liquid helium? Well, it's not an ionic bond, covalent bond, that's intramolecular, that doesn't count. There's no hydrogen, so there can be no hydrogen bonds. Helium has no permanent dipole. There are no positive metal ions in a sea of electrons in liquid helium. So here are two helium atoms. The little flashy green lights are indeed electrons and neutrons and protons in the nucleus. And if I slow time down and then stop it, you can see on the left-hand atom, the electrons and protons are on different sides, giving a temporary dipole to the atom. And those electrons repel the electrons in the adjacent helium atom and can lead to the formation of an induced dipole. And where you have negative next to positive, you will get an attraction, and that is the London Dispersion Force. It only lasts an instant, because the electrons are soon on their way again, and the attractive bond is broken. Looking down group 17, the halogens, literally giving birth to salt. Ooh, I bet that would sting. Notice the trend in boiling points there. Fluorine's a gas, but at the other end of the group is iodine, the solid. Why is that? Well, it's to do with London dispersion forces. The more electrons there are, the more London dispersion forces there are. And so iodine has more electrons than fluorine, and that has more London dispersion forces and a higher melting and boiling point. You need more energy to break those bonds, a higher temperature. So, London Dispersion Forces. Well, let's start with these Morningstar Farm sausages. Wow, that's about as disappointing as you can imagine. And then we've got veggie meatballs as well. Okay, they look a little bit better. So I'm going to pretend that these are pentane, and this is 2,2-dimethylpropane. So come over here and video the cooking.
Please.
Please. So you can see that the sausages and the meatballs have the same volume, but they do have different surface areas. This has a smaller surface area, it's a sphere, and this has a larger surface area. So the sausages, there are more points of contact between them, which means they're going to stick together more than the spheres that are only going to touch at very small points of contact. And the reason for that is that sausages have a larger surface area, meatballs have a smaller surface area. And it's the same with London Dispersion Forces. The pentane has a larger surface area, and the 2,2-dimethylpropane has a smaller surface area. So this is having a higher boiling point, and these are having a lower boiling point. Let's get in. Start the video. You know, actually, it tastes like 2,3-dimethylpropane. So looking at this animation, you can see two molecules. Both of them had the same volume, but they do have different surface areas. The spheres on the right only make very, very small contact with each other, which means that London dispersion forces are going to be much reduced compared to the sausage shapes on the left, where there's much more contact when they collide each other. And rather labouring the point, here is the boiling point of pentane. You can see that it is indeed elevated above the boiling point of 2,2-dimethylpropane. So in summary, London dispersion forces are the weakest intermolecular force. They're due to instantaneous induced dipoles. They're temporary, and they increase with increasing number of electrons, and they increase with increased surface area. The way I remember this is sticky sausage, non-sticky balls.